Next up, we have Chase Jakobi, who will be introduced by Rebecca Purvis.
Hi, everyone. Oh, this is a bittersweet day here to see all the hard work that you all have been doing this summer. We're all so proud of you. My name is Rebecca Purvis. I live in Dallas, Texas, and my areas of expertise are in solar physics and in space weather. And I had a blast this summer working with Chase Jakobi, who is a rising senior who lives near Chicago, which is in the same time zone as Dallas, which was great for getting together. So Chase is very passionate about math, science, and computer science. And so, really, they could have worked on any of the projects this summer. I am very glad that Chase threw the word heliophysics in their application because that's how they were paired with me. Yeah, so we worked this summer on a little bit of solar physics. We are in solar max, which means that there should be a lot of solar activity. And so I kind of had plans for us to monitor really intense solar storms and space weather events in real time, which is my background. But unfortunately, the sun was kind of quiet, and so we didn't get to do that in real time. But it kind of actually worked out. It was a little bit of a bummer, but also a little bit of a present because Chase was able to focus on another thing and go kind of in depth. And so, with that, I'm going to hand it over to Chase.
Let me share my screen. Okay. So, hi, my name is Chase, and over the summer I was investigating the unexpected behavior of solar cycle 25. So, once I get this all set. The sun, although the sun may appear to the naked eye as it did thousands of years ago as an unblemished circle in the sky, in reality it is far from perfect. The sun is covered in many different types of protrusions, indentations, and other phenomena that not only affect its visual appearance, but also the properties of its magnetic field. One example of such a phenomena is a sunspot, a small spot on the sun that is in fact a region of concentrated enhanced magnetic field in the lower solar atmosphere. These can be seen on this image of the sun from August 7th, 2025, as these dark points on the solar disk. These sunspots are the main focus of measuring the sun's activity. By doing a few simple calculations to the number of sunspots observed on the solar disk, one can find the sunspot number. This sunspot number oscillates once every 11 years in a process known as the solar cycle. However, predicting these solar cycles has proven to be challenging, and the methods used for prediction seem to be unreliable. For example, solar cycle 25, our current solar cycle, was predicted to be much less intense than the current measurements indicate. On a displayed graph from the National Oceanic and Atmospheric Administration's NOAA's Space Weather Prediction Center, the prediction is represented by the red line, and the actual data is shown by the black line. The purple line represents the smooth data, which is what we would expect to be close to the red line in an accurate prediction. Miscalculating the strength of the solar cycle can be an immense problem because we are an increasingly tech-based society. Solar anomalies affect what is known as space weather, which can affect satellites in orbit as well as instruments closer to Earth. Radio signals and GPS are just a few examples of everyday appliances that could be affected by a solar storm. A recent example of this is the failure of some of SpaceX's Starlink satellites in 2022, which burned up in orbit when Earth was hit by a geomagnetic storm. Since technology is so integrated into daily life, it is important to study and predict the timing and magnitude of these disturbances to keep our society functioning. To investigate this, I researched the solar cycle and the solar dynamo, the mechanism responsible for generating the sun's magnetic field. I was also monitoring the sun in real time using tools such as ISWA, the Integrated Space Weather Analysis, Donkey, the Space Weather Database of Notifications, Knowledge, and Information, and a space weather dashboard provided by NOAA. Early in the summer, I came across this coronal hole, which was imaged by the Solar Dynamic Observatory, or SDO, spacecraft using an image known as the Atmospheric Imaging Assembly, or AIA. A coronal hole is a common solar phenomenon. It is simply an area of the sun that is cooler and less dense than the surrounding plasma, and it is characterized by an open unipolar magnetic field. This can cause an increase in solar wind velocity, which in turn can affect space weather. As you can see, this coronal hole takes up a large portion of the solar disk. Since it also affects the sun's magnetic field, I began to wonder what effects coronal holes had on the sun's activity. In order to figure out what this impact could be, I created a variety of computer programs that ultimately allowed me to compare coronal hole area, which I figured would be proportional to its impact on the solar magnetic field, to the smooth monthly sunspot number. All of these programs are linked through GitHub on the QR code shown on your screen for those of you who would like to investigate them further. First, to get the coronal hole area from 2010 to 2013, I used an already existent Python code from online documentation from a library called SunPy to pull SDO images and detect any existed coronal holes. I coded additional methods to pull the area of the coronal holes detected and saved their areas into a table-like format known as a CSV or comma-separated values file. However, this method took a lot of time and computing power, even when I ran it on a virtual machine from Google Cloud. Luckily, to get the rest of this data, 2013 to 2025, ISWA provided a data tree with data from the Automatic Solar Synoptic Analyzer, or ASA, software system, which included data on the area of the coronal holes. Using Java and another virtual machine, I was able to save this information into another CSV file as well. Once both of those programs had ran, I manually combined the two files and standardized their units on a spreadsheet. I downloaded the spreadsheet as another CSV file, then used another Java program to combine these daily values into a monthly average. To further increase the usability of the data, I then used the same method that scientists use to smooth sunspot data, known as the taper boxcar running mean, to smooth my data. This method involves taking the average of the month in question, the 6 months prior and the 6 months after, with the first and last months of the average carrying a weight of 0.5 instead of 1. Lastly, I graphed this data in order to analyze it properly. So this is the data that my programs came up with. As you can see, the x-axis represents time and runs from around 2010 to present time. For reference, 2010 was around the beginning of solar cycle 24, which reached its max in 2014. Solar cycle 24 ended and solar cycle 25 began in 2019, and currently we are around the predicted maximum of solar cycle 25. The left y-axis, colored blue, represents the sunspot number in the standard units seen before. The right y-axis, colored green, represents the smooth monthly average coronal hole area in thousandths of a solar disk. There are a lot of interesting analyses that can be done with this graph, but perhaps the most compelling is the analysis of the peaks of both plots. As shown, the coronal hole area peaks around 40 prior to the max of solar cycle 24 and peaks again at 40 after the max. However, prior to the max of solar cycle 25, the coronal hole area only reaches a max of around 25. The current coronal hole area, at about solar max, is around 40 and presumably only going to rise, assuming that coronal hole area peaks after the sunspot number peaks. This leads to an initial hypothesis that the difference between the coronal hole area peak prior to solar max and the coronal hole area peak after solar max could possibly be related to the strength of the sunspot cycle. However, without more data, it is impossible to be confident in any conclusion, as the data set is too small and correlation is not causation. However, I am confident that coronal holes have an impact on the sunspot cycle. In order to convince you one final time that this relationship is more than just a coincidence, I would like you to look at this figure from a paper written by Kenichi Fujiki and others. Once again, the x-axis represents time, but in this case, the y-axis represents latitude, with the top of the figure representing the sun's north pole, the bottom representing the sun's south pole, and the center representing the equator. The background, represented by the yellow and blue haze, is a classic way of showing sunspot latitude known as a butterfly diagram, and it shows the migration of sunspots from higher latitudes to lower latitudes throughout the solar cycle. The blue and red X's in the foreground represent the location of coronal holes throughout the solar cycle. As you can see, there's a strong correlation between this location of sunspots and the location of coronal holes. This makes it immensely improbable that there would be no relationship between the two. As I said prior, I assumed that the effect of a coronal hole on the sun's magnetic field would be proportional to its size, which is a step past what this graph represents, but this is simply proof that my idea has validity, and that there must be a bigger connection between coronal holes and sunspots. So, in conclusion, the biggest takeaway from my research is that more work needs to be done. Without more data, no definitive connection can be made between coronal hole area and the strength of the solar cycle. However, I do think there is enough evidence to prove that a correlation does exist and that this correlation holds an important piece to the mystery of the sunspot cycle. I'd like to acknowledge my mentor, Dr. Rebecca Purvis, who has been so wonderful to work with over the course of the summer, Dr. Lynn Kaminsky, who is the heart and soul of this program and provided me with everything I needed to present here today, Ariana Arista, Sam Tumlo, and Wendy Martin, who helped run this amazing program and give me this opportunity, Mr. Michael Panisi, who wrote me an amazing rec letter that got me into this program and made me believe that I could be someone in science, Mr. Christopher Zickert, whose teachings helped more than I could have ever anticipated, Mr. John Noah, who has believed in me and pushed me, particularly in mathematics, and my teachers, family, especially my parents, and friends who believed in me and my abilities even when I didn't. So just really quickly, I'm going to flash up here are some credits for my research. Here are the credits for the images I used, and here are the credits for programs and software I used. And so now I will give it out. Thank you for your time, and I will now give it out to any questions. Okay.
Wow, what an amazing presentation. Great job,
Yep.
Chase.
Thank you.
Yes.
Any questions for Chase?
So have people, I'm not a heliophysicist, but have people written papers about this correlation that you're, trying to
I
measure?
haven't found any published presentations. There was that one paper that was looking at coronal hole location and sunspot location, but that was not focusing on the interconnectedness between the two, which I do find slightly odd. And I do think people are focusing on it, but there has been no published work as of yet.
Well, could be something to write up.
Right, which I would like Chase to present this work at a conference.
Which conference do you normally go to? AGU?
So there's AGU, there's AAS also has usually one session about the sun, and then in the summer there's another conference. It's called Shine for the sun.
Okay, well, if you want to go and have Chase accompany you, definitely let us know before we run out of money.
August has a question in the chat.
I would say that at least what I was focusing on is the idea that coronal holes could lead to sunspots. But like I said, with such a small data set, it's hard to say what causes what or what impact these things have on each other. I know they impact each other based on what I've found, but it's hard to say exactly what that impact is. So although my presentation was focusing on coronal holes impacting the sunspot number, it could easily go the other way.
Yeah, good point.